So far, we have learned two things. First, cavitation nuclei exist, and second, they survive because they are attached to microscopic dirt or corrosion particles. Now, let's go inside one nucleus. At first glance, it looks like an empty bubble, but it is not empty at all. It contains gas, mainly dissolved gas, and water vapor. These two together create the pressure inside the bubble. So, what's inside a nucleus? We all know to reach the state of equilibrium, the pressure inside the bubble must be equal to pressure outside. The formula shows the same thing. P inside is equal to P of gas plus P of vapor, which means P gas comes from trapped air like oxygen and nitrogen, whereas P vapor is the vapor pressure of water. Many people think vapor pressure appears only when water boils. Actually, even at room temperature, some water molecules continuously escape into vapor form. So, even a tiny cavitation nucleus contains water vapor. Together, these two pressure push outward on the bubble wall. Now comes the balancing force. Think of the bubble surface as a stressed rubber balloon. Every water molecule on the surface is pulling its neighboring molecule. So the liquid surface behaves like a stressed elastic membrane trying to reduce its area. That creates an inward squeezing force. Well, according to the Young-Laplace equation, P inside minus P outside is equal to 2 sigma by R, where sigma is surface tension and R is bubble radius. Notice something very interesting. Radius is in the denominator. As radius becomes smaller, the term becomes much larger. The term 2 sigma by R becomes much larger. Now, this is the point what most of the people skip. Let's imagine two balloons, or let's imagine two bubbles. One is of the radius 10 mm and one is the radius of 1 mm. Which one would require you to blow harder? Obviously, the smaller one. Why? Because of the surface tension. It squeezes much harder and therefore tiny nuclei have very high internal pressure. Now, imagine this nucleus traveling through a centrifugal pump. At first, assumption is that each nucleus contains a fixed amount of gas. Or in other words, we can say that during the short time the bubble moves through the pump and gas doesn't suddenly enter or leave the bubble. So we assume the gas mass remains constant. Since the amount of gas is fixed, it approximately follows the ideal gas law. And that means if pressure decreases, volume increases and vice versa. This is exactly how the trapped gas behaves inside the nucleus. Now combine the gas law with the pressure balance we discussed earlier. Suppose the nucleus enters the impeller eye where the surrounding pressure drops. The external squeezing force becomes smaller and the gas inside expands. The bubble volume increases. As volume increases, the radius also increases. Similarly, if the surrounding liquid pressure increases, the bubble shrinks. That's why the slide calls it a pressure sensitive balloon, because it does not decide its own size. Its radius continuously adjusts according to the surrounding liquid pressure. Now remember, at this very stage, the bubble has not damaged anything. It is only growing. The damage occurs much later. When the surrounding pressure becomes much higher than the bubble pressure and the bubble cannot withstand with that pressure, then it implodes. So the key idea is that a cavitation nucleus is always in a delicate pressure balance. Inside it, gas pressure and vapor pressure push outward, while surface tension and the surrounding liquid pressure push inward. Tiny bubbles have a much larger surface tension effect because of the Young-Laplace equation, making them more stable, but when the surrounding pressure drops sufficiently, they expand like tiny balloons. Later, when they enter a high pressure region, they implode. and that violent implosion is what causes cavitation damage. Alright, if you want more such interesting videos, visit our website www.capacira.com. Like, subscribe and share. Thank you so much.